So the goal of our lecture today, lecture 21 of this real analysis course, is to discuss the notion of uniform continuity. And I want to slide into the notion of uniform continuity in a more motivated way than the text does. So the way I'm going to get us to discuss uniform continuity is by first discussing the exponential functions. So given some positive real number b, and integer p and natural number q, we know how to define b to the p for any integer, right? So a positive integer, b to the p, is just doing repeated multiplication of b, p times. B to the 0 is 1, and b to a negative power is repeated multiplication with the inverse, the multiplicative inverse of b. And that just, so this is just using the basic axioms of the real numbers to define this. And then from the last lecture, we can also make sense of the qth root of b. So with these two things, that allows us to define an exponential function for any rational exponent. So if we take our p and q and form the rational number x, which is p over q, then we can talk about b to the x. So this is the exponential function with base b and exponent x. We can denote that b to the x, and we can define that to be the qth root of the pth power of b. And this is easily seen to be the same thing as the pth power of the qth root of b as well. So you can take that as an alternate definition. Easy to see that they're the same. And therefore, we have a function defined on the rational numbers taking values in the positive real numbers. Okay, so this is our basic exponential function. So our main goal is to extend this function as defined on the rationals to be defined on all of the reals. So for example, we want to know what, say, 3 to the square root of 2 to an irrational power. What does that mean exactly? I mean, it's not entirely clear how this is exactly defined. So we can't define it in sort of finite terms in terms of natural numbers and integers like we defined the rational power of a base, right? Because this square root of 2 is sort of fundamentally not definable in finite terms like that. So in high school, probably in pre-calculus or something, the way you would have discussed this b to the x function is, you would have graphed it for some rational values. Right? You take b and raise it to some rational values, and you get some sort of points plotted, right? And then you would just connect those points and say, oh, okay, so this defines the graph of b to the x, right? So this defines our function b to the x. But that doesn't actually really tell you, anything about how to find 3 to the square root of 2 or how to make mathematical sense of that. It kind of just is reliant on this intuitive drawing of this picture here. And so what we'd like to do is discuss this extension of this function from the rationals to the reals. So just note quickly that as stated here, extending this function from the rationals to the reals is actually trivial because we can just, all we need to do is make this extension a function, so we just kind of arbitrarily define it on the irrational numbers. But that, of course, is not what we mean. It's certainly not what's indicated by the pre-calculus picture that that we discussed just a second ago, because what we really want to do is kind of plug the holes in the graph of this function as defined on the rationals. So one way to read that is what we really want is to extend this to a continuous function on all of the reals. Okay, so we want to do a very particular extension of this function to the real numbers, very controlled extension. So before we get ahead of ourselves, let's just look at some basic properties of this exponential function that we've constructed so far. So for rational exponents, it's easy to show that the exponent laws hold. The familiar laws about multiplying two powers of a base and about taking iterated powers of a base. And so you can do this as an exercise, a little bit tedious but elementary. Another property is that, of course, the exponential function when the base is 1 is just identically the constant function. But when b is in the range 1 to infinity, this exponential function is increasing. In other words, when x is less than y, b to the x is less than b to the y. And then it's decreasing on 0 to 1. So if x is less than y in 0, 1, if b is in 0, 1 and x is less than y, then b to the x is greater than b to the y. Okay, so these are, again, this is an pretty easy exercise. Another not too difficult property to establish is that the limit as n goes to infinity of b to the 1 over n is equal to 1. So taking continued roots always leads you to 1. So the proof of this is interesting. The case when, so b equals 1 case is trivial. So let's assume that b is greater than 1. Then what we can see is that, so since b to the x is increasing, and 1 over n plus 1 is less than 1 over n, it follows that b to the 1 over n plus 1 is less than b to the 1 over n. So b to the 1 over n is a decreasing sequence. But also the sequence is bounded from below. But since b is greater than 1, b to the 1 over n is greater than 1 for any n. So we have a bounded decreasing sequence. So therefore, the monotone convergence theorem implies there is a limit. Implies b to the 1 over n converges to some limit, say alpha. Or maybe we have b, so we'll just call it beta. But then we can use a trick that we've used before, which is that you can look at a particular subsequence. So if you look at the sort of even subsequence along here, that's going to converge to the same limit. However, b to the 1 over 2n converges to beta as well. And so we have beta is equal to the limit as n goes to infinity of b to the 1 over 2n, which is equal to the limit as n goes to infinity of b to the 1 over n square root. That's equal to the limit as n goes to infinity of b to the 1 over n to the 1/2, and that is just equal to beta to the 1/2. So beta squared has to equal beta, i.e. beta is equal to 0 or 1. But since b to the 1 over n is bigger than 1 for all n, beta must be bigger than or equal to 1. So therefore, beta, which is our limit, is equal to 1. So that's the b greater than 1 case. So if b is between 0 and 1, then 1 over b is bigger than 1. And it's easy to use this to get the same conclusion. So it's easy to get the conclusion from the previous case. And I'll leave you to work that out if you'd like. Okay, so we just use the previous theorem with 1 over b as our b, and you'll see that it works out. Okay. So now these propositions lead to a more serious proposition, which is that the exponential function defined in the rationals here is continuous. Okay, so let's look at the proof. The b equals 1 case is trivial because e sub b is just a constant function, which is clearly continuous. So we'll assume that b is greater than 1 for the moment. So the basic idea here is if we have to prove that the exponential function here is continuous at some c, then we have to look at the difference between b to the x and b to the c, right? And all we have control over is x minus c. So we want to say when x minus c is small, that this thing is small. And so one way to get an x minus c involved here is to factor out a b to the c. So this is going to be b to the c. That's always positive, so we don't need the absolute value. B to the x minus c minus 1. So this is just some constant here, and we want to be able to make this thing less than epsilon, right? So we want to be able to make this quantity small here, b to the x minus c minus 1. We want to be able to make that thing arbitrarily small as long as x minus c is arbitrarily small. But that's just to say, if our x minus c is arbitrarily small, that says x minus c is close to 0. So we want to say if we have something close to 0 and we take b to that power, the difference between that and 1, we want to make that small. But that's just equivalent to the continuity of this exponential function at 0, right? Because so if we look at b to the y minus b to the 0, that's b to the y minus 1. Right, so if we want to say if the distance between y and 0 is small, we want to control b to the y minus 1. That's just talking about continuity of this exponential function at 0. But that's exactly the situation we have here. We have this x minus c quantity, which is going to be small, which is close to 0, and we're trying to control the exponential of that quantity minus 1. So really all we need to show continuity at any given c is to just have continuity at 0. Okay, so the argument for continuity of this function really just comes down to continuity at 0 in some substantial sense. So we'll just, we first argue that e sub b is continuous at 0. And where this is going to come from is our previous proposition. Right? We have this limit, so we have this one particular sequence of b to a power. So we have these 1 over n's which are going to 0, right? They're converging to 0, and we have b to them. So the function along there is also converging. The function is converging to 1. And since 1 is b to the 0, this statement looks quite a bit like it's relevant to having continuity at 0. Okay, so what we need to do is we'll let epsilon greater than 0 be given. So since we have b to the 1 over n converging to 1 and b to the minus 1 over n converging to 1, and because this is just the same thing as b to the minus 1 to the 1 over n, but b to the minus 1 is just another b, right? So we just have a different b with 1 over n, so that's also converging to 1. So those things both converge to 1, and so with this epsilon greater than 0 given, so there must be an n. There is an n such that when n is bigger than or equal to n, we have we have b to the 1 over n. See, our b is bigger than 1 here, so any power of it is bigger than 1. So b to the 1 over n is always bigger than 1. So we just have this difference is less than epsilon, and the b to the minus 1 over n, that's 1 over b to the 1 over n, so that's going to be less than 1. So we'll have 1 minus b to the minus 1 over n. That's a positive quantity, and that is small. That's less than epsilon. Okay, so each of these sequences for the given epsilon, this one has an n1, this one has an n2 with this property, and then you take n to be the maximum of them. Okay, so hopefully that's all right. And then sort of the basic idea here is just that if you look at this, so you have negative 1 over n over here, you have 1 over n here, your b to the 0, so b to the 0 is equal to 1, right in the middle there. So b to the 1 over n is like here, b to the minus 1 over n is here, and what we have is that these gaps, the vertical distance here is less than epsilon, right? So this distance here, this is less than epsilon, and this distance here is also less than epsilon. And then we have kind of the graph of this function over the rationals. It's increasing, right? So if we take anything in here in this interval between negative 1 over n and 1 over n, it's going to have to fall somewhere between these b to the negative 1 over n and b to the 1 over n. Right? So it's going to fall somewhere in here, be one of these like orange dots. And so its distance between, the distance between it and 1 is also going to have to be less than epsilon. Right? So so the values of b on these endpoints are sort of the extremities. Everything else is in between. So this exponential function at any value in between here is going to be closer to 1 than either of those endpoint things. And this just comes from the fact that this function is increasing. Okay, so the increasing is going to tell us that we can just take our delta to be 1 over n here. All right, so that's the basic picture that goes with this. So now with this in place, so let delta equal 1 over n. And suppose that that x is a rational number, and the distance between x and 0, in other words, the absolute value of x, is less than this delta. Well, then, as in the picture, since delta is 1 over n, this just means we have negative 1 over n is less than x is less than 1 over n. So since b, or let's say e to the b, so since e sub b is increasing, b to the negative 1 over n is less than b to the x is less than b to the 1 over n. So thus 1 minus b to the x, well, b to the x is bigger than this, so that means when we subtract b to the x, that's going to be smaller than 1 minus b to the negative 1 over n, and that is less than epsilon. And also b to the x minus 1, on the other hand, b to the x is less than b to the 1 over n, and b to the 1 over n minus 1 is less than epsilon. So the absolute value of b to the x minus 1, which is equal to b to the x minus b to the 0, is less than epsilon when x is less than delta in absolute value. Okay, so this proves continuity at c equals 0. Okay, so now we argue continuity at a general c. So as I said before, so we're going to let epsilon be greater than 0. So what we have to do is look at b to the x minus b to the c. We have to control this. This is just b to the c times absolute value b to the x minus c minus 1. And by the continuity of this exponential function at 0, as long as x minus c is sufficiently small, we can make this quantity here as small as we like. In particular, we can make it less than epsilon over b to the c. All right, so that'll give us our epsilon here. So all we have to do is, since e sub b is continuous at 0, there is a delta such that when, let's say, y is rational and has absolute value less than delta, it follows that we just want b to the y, the difference between b to the y and 1, to be less than e to the epsilon over b to the c. So we just need epsilon over b to the c. That follows that b to the y minus 1 in absolute value is less than epsilon over b to the c. So then if x is within delta of c, we have, and I guess we'll say, if x is within delta of c and x is rational, of course, we have that b to the x minus b to the c, now we're just repeating the same computation again, is equal to b to the c times b to the x minus c minus 1 absolute value. And we know that this is one of our y's, right? So that means our b to the y minus 1 is less than epsilon over b to the c. So this is less than b to the c times epsilon over b to the c, and that is equal to epsilon. Okay, so we have continuity. So far we have continuity of e sub b when b is in this interval from 1 to infinity inclusive. So if in the case where b is between 0 and 1, e sub b of x, you can just check this, right? You're just writing b to the x is b to the minus 1 to the minus x. So this is just e sub b to the minus 1 of minus x, right? Where b to the minus 1 is in the interval from 1 to infinity. So thus, e sub b is a composition of continuous functions. Right, you first negate and then you do this continuous function to do this function. So we have a composition and that's continuous. The composition of continuous functions. And thereby continuous. Okay, and that completes the proof. All right, so let's return to the discussion we were originally having, which is we want to extend the exponential function of base b defined on the rationals to a continuous function, right? So now we know we have this continuous function on the rationals. We want to extend that to a continuous function on all of the reals. So how do we do this? Okay, so we need some idea of how to do this extension. So how do we do this? Well, there's a more or less natural idea, which comes from the fact that since this extension is to be a continuous function, it has to respect limits. Right? If we look at a sequence limiting and we look at the if we apply the function along that sequence, then the function values have to be converging to the value of the function at the limit point. But every real number is a limit of rationals, right? So we can take, so if we take a rational sequence which converges to some x, then this extension function, it has to be the case that the exponential of those rationals, b to those rationals, is converging to b to the x, whatever that b to the x is to mean. But we know what the exponential on those rationals means, so that suggests defining the exponential of x with base b to just be the limit of those rational exponents. Okay, so that seems to be the natural idea. So then the basic question is, does this procedure make sense? So at a first glance, it seems like maybe it does. And so these rationals are converging to x, so the rationals are getting very close together, right? They're crowding up around x. And so if you got these rationals getting close together, then we have this continuous function on the rationals, right? So shouldn't their function values also be getting close together? And we have this continuous function sort of takes things which are close together and gives you outputs which are close together, right? Isn't that kind of the meaning of continuity? Well, in fact, this procedure is going to work in this particular example, but in general, we kind of need to be careful. Our reasoning here, as stated, is not quite correct. So to see this, we're going to look at a couple examples. So let's consider f of x to be the function which is 1 when x is greater than 0 and negative 1 when x is less than 0. Okay, so this so f is a continuous function on the domain A, which is the real number is minus 0, often denoted r star. This is r minus just the point 0. So you have a continuous function on this domain, but there's no way to extend it to a continuous function on all of r. However, any definition of f of 0 yields a function which is not continuous on R. Okay, so even though we have a continuous function here, so you should think by analogy. So this function here is like our function, our exponential function defined on the rationals, which we're trying to extend to the reals. So here we have, again, just a continuous function defined on some domain. We'd like to extend it continuously to the reals, but we cannot. No matter how we try to define f of 0, it's not going to be a continuous function. And so, one way to see this, so for example, so to see this, right, so what we can do is, if we're kind of thinking in the mode of what we were trying to do above, we can take try to take a Cauchy sequence, which is converging to 0, right? So take a sequence going to 0 and try to define f at 0 as the limit of that sequence. But there are sequences that you can take going to 0 for which that limit doesn't make sense. So what we can do is consider xn equals -1 to the n plus 1 over n. Then xn, the sequence converges to 0, but f of xn can't converge to f of 0 for any value of f of 0, since the sequence f of xn, right, is just an alternating sequence of 1s and -1s, so that doesn't converge at all, since that sequence doesn't converge to anything. Okay, so even though we have this function, it is continuous on this domain. It's continuous in such a way that it cannot be extended to all of the real numbers. And another example, which is handled very similarly, is just g of x equals 1 over x on the same domain, real numbers minus 0. So this has the same property as f above, cannot be extended to the real numbers continuously, even though it's continuous on its domain. So this is continuous on its domain, is continuous, but cannot be extended to R continuously. Okay, for much the same reasons, so I'll leave that to you if you want to look at the details. All right, so we have these two functions here, which are perfectly continuous on their domains, but they cannot be extended any further than that and maintain continuity. But we know we have this exponential function that we're investigating, which is continuous on the rationals, and we do know, from our intuition, from our experience in pre-calculus, that this is going to be extendable to a continuous function on all of the reals. So what's the difference between these two continuous functions? We'd like to somehow put our finger on something that distinguishes these two types of continuous function. So to do that, let's sort of look at what's wrong with these first two functions that we looked at, or these two example functions, f and g. So here's the graphs of each of these functions. Now, each one of these functions has the property that by continuity, right, they're continuous in their domain. So if we take some c in the domain of the function, and we take points close to that c, right, so we maybe have some sequence of points getting close to c, then the images are all close together, right? So f of c is here, and actually in this case, kind of boring, all the images are have exactly the same value. And here, if we get points coming close to C, all the images are close together, right? However, this is not the case. This is not the case for all points. Okay, so it's only when you have points that are getting close to a particular point in the domain of the function that the function values are staying close together. So, for example, in this first function, when you have points that are close together but gathered around 0, right? So if your points are on both sides of 0, then you have some of the points going to 1 and some of the points going to -1. And so those images are far apart, despite the fact that the points themselves are close together. And so these are all huddled close together here, but their images are getting sort of arbitrarily separated. And similarly, if we take points that are bunched up close together near 0 in this function down here, for example, you can consider the points 1 over n, then their images are far apart, right? They're spaced 1 apart. So the 1 over n's get turned into just n's, and they're separated by 1 each. So they're not getting close together. Okay, so in each of these functions, we have the property that you can have inputs that are close together, so very close together, but their outputs are actually far apart from each other. They're not getting close together. So that kind of separates them from the exponential function that we're looking at. So it turns out with our exponential function that we're looking at, as long as the inputs are close together, then the outputs are going to be close together, no matter what those inputs are. So no matter what rational inputs we have, the outputs are going to be close together as long as the inputs are close together. But these functions, despite being continuous on their domains, there's ways for points to gather close together without their images being close together. So the next definition is meant to describe a stronger form of continuous function. So a function which is continuous in a way that rules out these two examples, f and g here. Okay, so here's our definition that describes this stronger form of continuity for which the bad behavior of those f and g examples above does not occur. So we have some function defined on a domain in Rm, taking values in Rn. We say that f is uniformly continuous on A if for any epsilon greater than 0, there is a delta such that when you take 2 points in A which are within delta of each other, then their images are within epsilon of each other. So in other words, if x and y are close together, and delta measures quantitatively this notion of closeness, so as long as x and y are close, then f of x and f of y are close together. Okay? To get a better feel for this definition, let's compare it to the definition of continuity again. So same setup, or the definition of f being continuous on this domain A is that for any point in A and any given epsilon greater than 0, there's a response delta such that when x is in A and within delta of C, it follows that the distance between f of x and f of c is less than epsilon. Okay, so in other words, when x is close to c, then the output values f of x and f of c are close. Okay, so you sort of immediately see from this, so it's immediately apparent that uniform continuity implies continuity. So uniform continuity on A implies continuity on A. And for this, just take C to be equal to Y. So take y equals c in the definition of uniform continuity, and you just end up with the definition of continuous on A. Okay, so uniform continuity is strictly well, it's stronger, at least than continuity on A. It's stronger in the sense that it implies continuity on A. So then the question is, well, what's the difference then? What's the difference between uniform continuity and continuity? Well, the main place where the difference comes in is this C here, which happens along with the epsilon greater than 0. So in the definition of continuous, you're given C and epsilon, whereas in the definition of uniformly continuous, you're only given epsilon. Okay, so in the definition of continuity, your delta here is responding to a given C and epsilon. In uniform continuity, your delta is only responding to epsilon. So another way to put it is that delta in the definition of continuity is allowed to depend on C. Okay, so we're just saying f is continuous on A means that f is continuous at every C. So we look at each individual C, we have an epsilon challenge at that C, and we have to respond with a delta, right, to that epsilon challenge at C. So this delta is conditional on C, potentially. It's allowed to depend on C. But we might have a different delta for every C, right? So for each C, we're given an epsilon. We have to find a delta at that C for that epsilon. We move to a different C, it might end up for the same epsilon being a different delta. But that's not how uniform continuity works. So for uniform continuity on A, it has to be that for any epsilon, you have to respond with the delta so that when x and y are close by delta, then the images are close by epsilon. In continuity, you have a C given to you ahead of time, and then you just have to say when your x is close to that particular C, then the images are close. In uniform continuity, it's as long as the inputs are close together, the outputs have to be close together. Okay, so for continuity, it's close to a particular point, means outputs are close together. For uniform continuity, it's inputs close together, full stop, has to imply that outputs are close together. Okay, so that's the definition of uniform continuity. Basically, uniform continuity, the same delta has to work for every point. Right? So you think of this y here as kind of a variable C in your definition of continuity. So the same delta has to work for every C, right? So for each y and A, you have to have the same delta response to an epsilon challenge at y. Whereas in continuity, you're allowed to have a different delta response to the same epsilon for different C. But in the uniform definition, your delta response has to be uniform over that given epsilon. Okay, so that's where the uniform comes from. Okay, so I've written down here the summary of the answer I just gave. So it again is just that in the definition of continuity, your delta is conditional on the C and the epsilon. So in brief, your delta is allowed to depend on C, and you can have different deltas for the same epsilon challenge as you vary C. But in the definition of uniform continuity, there needs to be a uniform delta response to each epsilon challenge, which works at any point of A. All right, so let's look at a bunch of examples to make sure that this definition is clear and it's clear how to work with it. So let's look at f of x equals x squared. So I claim this is uniformly continuous. Uniformly continuous on the interval negative m to m for any m greater than 0. Okay, so here's our proof. This is an epsilon delta thing. So you have an epsilon challenge. Right? You basically are claiming that values of this function stay close together as long as the inputs in this interval are close together. So somebody's going to challenge you with an epsilon, say, I bet you can't make them within epsilon of each other, and you have to respond by saying, well, yes, as long as they're within this distance delta of each other, it's going to work out. So we have to let epsilon greater than 0 be given here. And we have to figure out how to respond. So what we do is some scratch work. Right? We look at the difference of f of x and f of y. We want to say our outputs are close together as long as we control how close our inputs are together. We do some simple algebra here. And what we have control over is this. We don't have control over this until we remember, well, we can just sort of estimate this away. So x plus y can't be any bigger than 2m by the triangle inequality. So this is less than or equal to absolute value x plus absolute value y. And absolute value of x, absolute value of y are both less than or equal to m. So this is less than or equal to 2m times the distance between x and y. And of course, we can make this less than epsilon by just making the distance between x and y less than epsilon over 2m. Okay, so what we'll do is respond. So set, let's say set delta equal to epsilon over 2m. Then if x and y are in this interval, and x and y are less than delta apart, then it follows that. Actually, this is perfect. My scratch work serves as a proof. Don't even have to touch it. Okay, so just recopy the scratch work and maybe just tidy up a little bit here. This is less than, now we have our delta, which is epsilon over 2m, and that equals epsilon. Okay, so we have uniform continuity. Okay, so you notice our delta here doesn't depend on any particular point. It just depends on the whole set here, right? So our delta depends on epsilon and the set, in the sense that our set was presented in terms of this number m. So we have that m showing up in the delta. So this uniformly continuous sort of depends on the domain. And I'll illustrate that with the next example. So the next example is the same function, f of x equals x squared. This is not uniformly continuous on the whole real line. Okay, so let's look at the proof. So if this is not uniformly continuous, then the skeptic is going to win their challenge, right? So they're going to be able to produce an epsilon that you can't beat. And so in this case, we're just going to let epsilon be equal to 1. Or so maybe I should say choose epsilon equal to 1. So basically the point is that if we allow ourselves to take our x and y from the whole real line, for this epsilon equal 1, I can find x and y that are very close together on the real line, but are so x and y can be sort of arbitrarily close together, but their image be separated by 1. And the reason is because x squared grows very fast when x is very large, right? So as long as we take our x large enough, then when we move over from x a little bit, we're going to see values of the function increasing by more than 1, just because this x squared, the squaring, gets really powerful when our inputs are large. Okay, so how this is structured here is that we have this epsilon equal 1. This is the skeptic's going to win his challenge, so we're going to lose, and that means that no matter how hard we try, so no matter what delta greater than 0 we try, we can always find x and y within delta, but the images under the function are separated by at least this epsilon. Okay, so we can't beat this epsilon no matter what delta we pick. So let delta greater than 0 be given. or maybe I should phrase this as take any delta greater than 0. All right, so we're trying to respond with a delta, but we're going to fail. Take any delta greater than 0. We just have to find x and y that are close together within delta of each other, such that the difference in the function is greater than or equal to epsilon. So what we can do is we'll take x to be some large positive number. Right, so we'll take x to be very large. And y is just going to be x plus delta over 2. Okay, so y is going to be within delta over 2 of x, and then let's just look at x squared minus y squared, the difference between the outputs, to figure out what this x should be. And this should be simple. It's just going to get, when you square the y, you're going to get an x squared, which is going to get canceled off by that x squared. And then you're just going to have like the FOIL terms remaining. So you're going to have delta times x plus delta squared over 4. And this is positive, so I can kind of ignore it. I just want this difference to be bigger than or equal to 1. So this is bigger than delta times x, and this will be bigger than or equal to 1 as long as x is bigger than or equal to 1 over delta. Okay, so as long as I can take x to be 1 over delta, and then I'll take y to be that x plus delta over 2, and that should work. So we're going to consider x to be 1 over delta, and y to be that x plus delta over 2. So then x and y are within delta of each other, but their function values are not close together. But x squared minus y squared is equal to delta x plus delta squared over 4, which is bigger than delta x, which is equal to delta times 1 over delta, which is equal to 1, which is bigger than or equal to epsilon. All right, so we couldn't beat the epsilon challenge. And so that concludes the proof that x squared is not uniformly continuous on R. Okay, so you see the domain matters. When we restrict x squared to any closed and bounded interval, maybe you want to file that away for later, we have uniform continuity, but we do not have uniform continuity on the larger domain of all the real numbers. So let's look at one of those examples that we looked at above. So example, let's look at g of x equals 1 over x. This is not uniformly continuous. Not uniformly continuous on the non-zero real numbers. Okay, so let's try to prove this. Again, we can just let epsilon, or choose epsilon equal to 1. So the skeptic can choose epsilon equal to 1, and we're going to fail. So basically, you know, what this 1 over x function looks like, we'll be able to find, there's always going to be x and y close together near 0, whose images are separated by more than 1, right? So, and that's kind of intuitively obvious. So we're just kind of writing that down in a more rigorous way. And then we'll just copy the format of the previous proof. So take any delta greater than 0. And what we have to consider is we're considering the difference between 1 over x and 1 over y, which by getting a common denominator is just this quantity here. So again, the basic idea is we're just going to look at this part of the graph here, and when x is 1, this is 1, right? And so we're just going to try to take our x and y in here close enough together that they're within delta of each other, but so that their images are far apart. So let's see here. So if so there's kind of two cases. Like, I mean, the generic case is when this delta is really small, and in that case, we're going to have to make sure we take our x, very close to 0, and then our y very close to that x to make this all work out. But a general delta doesn't have to be particularly small. It could just be 1. So in that case, if your delta is bigger than or equal to 1, then you can take any x and y in this interval between 0 and 1. That would work. So to kind of cut down on a little bit of the complexity of thinking here, let's just suppose delta is bigger than or equal to 1. Then we can just take x to be 1 and y to be 1/2. These satisfy that the distance between x and y is less than delta, but then the function values, the function values are 2 and 1, and those are 1 apart. But 1 over x minus 1 over y is equal to 1, and that's bigger than or equal to epsilon. So suppose that delta is between 0 and 1. So now we're going to try to pick our x depending on that delta. And again, we have the quantity x minus y over absolute value x, absolute value y. And what we can do is make our x to be delta. So x is going to be delta. Delta is between 0 and 1, right? As delta gets smaller, this x is getting closer to 0. That's what we want. And we can make y equal to half of x, right? So delta over 2. And then it's easy to see from this thing that works out because the numerator is going to be delta over 2. The y part, that's going to be delta over 2, so that's going to cancel, right? And the x is going to be delta. And because delta is between 0 and 1, 1 over delta is bigger than 1. And that's equal to epsilon. So that's going to give us what we need in this case. So we can take x to be delta and y to be delta over 2. Then we have x minus y less than delta over 2, well, equals delta over 2, which is less than delta, but 1 over x minus 1 over y. Well, actually, I guess we don't even have to do the common denominator thing. This is just the difference between 2 over delta and 1 over delta. So that's just going to be 1 over delta. That equals 1 over delta, and that is bigger than 1 because of where how delta is situated, and that's equal to epsilon. So in either case, we're going to lose this epsilon challenge. You can always find x and y within the delta such that the function values are separated by that epsilon. However, we can see that this function is uniformly continuous if we keep ourselves away from 0. So is uniformly continuous. So again, need to emphasize that this depends on the domain. This is uniformly continuous on negative infinity up to some finite m, negative m, union m to infinity for any m greater than 0. So to see this, we let epsilon be greater than 0. And then again, just as before, we had the x minus y over absolute value x, absolute value y. And we can control this. We just need to somehow control that. So we need, some control over 1 over x. We need to say that's less than something. In other words, that the absolute value of x is bigger than something. But of course, if your x and y are in this domain, then their absolute values are bigger than m. Right? So we're going to have an m squared down here. So we're going to have our distance between x and y over m squared. So we'll need the distance between x and y to be less than epsilon, m squared times epsilon. So that'll be our delta. So we choose, so take delta to be m squared times epsilon. So you notice this delta is getting smaller, shrinking to 0 as m goes to 0, right? So the closer m is to 0, the more extreme delta response you need to an epsilon challenge, which sort of jives with the fact that this function is not uniformly continuous if we take m all the way to 0. So then if x and y are in A and x and y are within delta of each other, then in particular, the absolute value of x and the absolute value of y are bigger than or equal to m. So we have that the distance between 1 over x and 1 over y is equal to distance between x and y over the product of those absolute values. So that's less than delta over m squared, which is equal to m squared epsilon over m squared, which is equal to epsilon. Okay, so we have uniform continuity as long as we keep ourselves strictly away from 0. Now, circling back to where we started in the lecture, e sub b of x is uniformly continuous. It's uniformly continuous on the rationals intersect any interval, any bounded interval for any m greater than 0. Okay, so as long as we restrict the sort of extent of the rationals that we're looking at, we get uniform continuity. So we have uniform continuity sort of across any of the rationals in here, right? So we don't have this problem that, we're not going to have this problem that as we have a sequence of rationals going to some irrational number, right, that those rationals are getting close together, but the images are getting far apart. That is not happening. So this is kind of demonstrating that this function has a nice property with respect to convergent sequences. So those convergent sequences, as they get close together, their images are going to get close together, and that's going to let us define this exponential function on all of the real numbers. It's going to allow us to extend our function. So our proof here is that, so we're just going to have, we have b to the x minus b to the y. What we're going to do is pull out, just like we did with the continuity proof, pull out b to the y. We have b to the x minus y minus 1. And we know that we can, that we know by continuity of this exponential function at 0 that as long as x minus y is small, we can make this thing small. So we just need to get control over this b to the y, which is variable. But you see, y is in this interval from negative m to m. So the largest that b to the y could be, so b to the y is less than or equal to either, so it's b to the m if b is bigger than 1, and it's b to the negative m if b is less than 1. And yeah, so that's because this exponential function is increasing in this case, right? So we get the biggest value of this exponential at the right endpoint, and it's decreasing in this case, so we get the biggest value at the left endpoint. And I guess we can just say greater than or equal to 1. The b equals 1 case is kind of trivial. So in either case, call this constant c. Then this is less than or equal to c times b to the x minus y minus 1. And then by continuity at 0, we can choose our delta such that this second thing is less than epsilon over c. Okay, so the proof is going to be let epsilon greater than 0 be given. By continuity of e sub b at 0, there is a delta such that when the length of z, when the absolute value of z is less than delta, that implies that b to the z is within epsilon over c of 1. And we have to define what that c is. Okay, so now I've said what epsilon is. It's going to depend on c. So where c equals b to the m if b is bigger than or equal to 1, and b to the minus m if b is less than 1. Okay, and then we just show that this works. So then if x and y are in A and x and y are within delta of each other, it follows that f of x and f of x and f of y, that's e to the b to the x and b to the y, that's equal to b to the y times b to the x minus y minus 1, and that is less than or equal to, or well, I guess I could say less than c times epsilon over c, which equals epsilon, where we used that e sub b is increasing / decreasing for appropriate b values to say that b to the y is less than or equal to c. Okay, and that completes the proof. So now our last little goal before we end this lecture is to see how this uniform continuity of our exponential function on the rationals allows us to define b to the x as the limit of b to these rational numbers, where we have this rational sequence converging to x. So we want to say that this limit of b to these rationals makes sense. So basically, when we have a limit here in the domain, then the limit of the images of the Ri also exists. And that is addressed by the next proposition. So we have a theorem that if we have a function defined on A, and it has the property that it's uniformly continuous on A intersect with any large ball, and so a ball of any radius, then if you have a Cauchy sequence in A, the image sequence is also Cauchy. Okay, so this is useful for us because we showed that our exponential function is uniformly continuous as long as we take our rationals and we intersect with a large ball. Okay, so we have uniform continuity on this intersection of the rationals with a ball, and so that's exactly the situation we're addressing here. So we'll show that as long as we have a sequence of rationals, like there are Ri up here, so a Cauchy sequence, so a converging sequence is a Cauchy sequence, then the image sequence is also a Cauchy sequence and therefore convergent. So then this limit of b to the Ri's will make sense. Okay, so this is just the general statement. Okay, so since xk is Cauchy, it is bounded and thus contained in a large ball, contained in some BR0. So what we want to say is that this image sequence is Cauchy. So in order to do that, we need to let epsilon be greater than 0. Now, what we have is uniform continuity of our function on this ball, right? As long as we're looking at the stuff in the ball that's in A. And the xk is some stuff in A that's in that ball. So what we're going to do is invoke the uniform continuity of our function f. So with this epsilon given, so by the uniform continuity, of f on A intersect this ball, there is a delta such that x and y being in the ball and in A and within delta of each other implies that the images are within epsilon of each other. But we can make this Cauchy sequence, right, be within delta as long as we take our indices sufficiently large, because that's what it means to be a Cauchy sequence. It means as you go far out in the sequence bunches up, right? So it'll bunch up within delta. And then we'll be able to say that the function values of those x's are within delta as long as they're within or within epsilon as long as they're within that delta. So since this sequence is Cauchy, there is an n, a natural number, such that when k and L are bigger than or equal to n, we have that xk and xl are within delta of each other. But xk and xl are also in A intersect this ball. And thus it follows right, so there are two things that are in this ball intersect A, right, and they're within delta of each other, so therefore their f values are within epsilon. And thus it follows that f of xk minus f of xl, they're within epsilon. And so that is KL bigger than or equal to n implies that f of xk minus f of xl is less than epsilon. So the f of xk sequence is Cauchy. So an immediate consequence of this theorem is that we can define our exponential function for irrational numbers now by taking a sequence of rational numbers which converges to that irrational, and then setting b to the x to be the limit of the b to the ri sequence, because this is a Cauchy sequence, and we have the uniform continuity of q on those bounded subsets, right? So we take q and intersect with, there it is. So we take q and intersect with that, we have uniform continuity, and so by the theorem, our function has to take Cauchy sequences to Cauchy sequences. And so our b to the ri is a Cauchy sequence, so it converges, has a limit, and that can serve as the definition of b to the x. So there are remaining questions, though. So the first one, possibly the gravest question, is this well defined? That is, does it depend on the rational sequence? Does it depend on the sequence Ri? So in other words, right, so I just took a random rational sequence that converges to x, but there's going to be other sequences which converge to x. So does that give us the same definition? So does that give us the same b to the x value? And then 2, we would like to know if this resulting b to the x function is continuous. So if so, is b to the x continuous on R? And for the answers, you'll have to wait till the next lecture. All right, so I'll see you soon.